So I want to find the rotational kinetic energy of a rolling object, but in order to derive that formula, we have to, I want to review the center of mass definition and then go from there. So remember, by definition, the center of mass, if you have here's the x, here's the y. Let's say you have an object, right, in general. In our case, we want our object to be nice and circular so it can spin, but in general, by definition, let's say this is, you divide the object into many masses, and you call this one here mi, and the position of that m, the position from here to this mass is ri, okay, ri, and of course this has an x and a y component, so to find the center of mass, r of the center of mass was equal to the mi, let me just write it this way, m1 r1 plus m2 r2 plus dot 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 divided by m1 plus m2 plus dot dot dot, and we put a shorthand notation for this as the sum over I equal to 1 to capital N of mi ri divided by the sum over all the masses I equal to 1 to n of mi, and this is just the total mass, so it is 1 over the total mass, capital M symbolizes the total mass. This is I equal to 1 to n over mi ri. All right, that's the definition of the center of mass. Sounds good. I will refer to this in a moment. Now, let's say our object here is rolling. So here is my object, and this is x, this is y, and let me draw it a little bit farther. Draw it here, and my object is rolling, and it's moving this way. All right. So what's the position of this? I will divide the object into many little masses, and I want to know what the position of each mass here is r I. I'll put here this mass, the position of this mass relative to the ground, I'll put here ground, ri relative to the ground, and so the velocity of I, so the position of this mass mi here, mi relative to the, just mi. What's the position of mi relative to the ground is just ri relative to the ground. And so the kinetic energy of little mass is 1/2 mv squared. So the kinetic energy of just one mass will be 1/2 of that little mass times the velocity of that little mass relative to the ground, velocity of I relative to the ground, the velocity relative to the ground squared, right? Okay. And if you want the total kinetic energy, the total kinetic energy will be the sum of all the kinetic energy of all the ki, where I from 1 to n. I will ignore that part. I will just not write it. And so it becomes 1/2 of the sum over I of mi vi relative to the ground squared. Now, how do I calculate this? So I will do it the following way. What's the location of this relative to the ground? Well, it's equal to the location of the center of mass relative to the ground, and then the velocity of this object relative to the center of mass. So this is the position of the center of mass relative to the ground. I'll just put it, I could put center of mass relative to the ground, but just position of the center of mass, and understanding that it's relative to the ground. And this is the position of this mass relative to the center of mass. So the position of mass I relative to the center of mass. So we add the two vectors together. So if you add the two vectors together, you get Ri, right? How do you get from here to here? Well, you can go this way and then this way, or you can go straight. I'm interested in adding these two vectors and seeing what happens, because that's when things will, when you include the center of mass, things simplify. That's why the center of mass is defined the way it is defined. So first of all, let's notice that, I will get to this second. Let's notice that, actually let me do that on the whiteboard. On the whiteboard, and then we'll come back to here. Right here, Rig relative to the ground is equal to R relative to the center of mass, the position of the center of mass plus the position of this I relative to the center of mass. So I have this Ri relative to the ground will equal to Ri relative to the center of mass plus the position of the center of mass relative to the ground, right? Remember when you had when we did relative motion, we talked about this. So let's get the velocity. The velocity will be the derivative of this. The velocity of I relative to the ground will equal to, take the derivative of this, it would be the velocity of I relative to the center of mass plus the velocity of the center of mass. Just take the derivative. Okay. And so this formula includes Vi relative to the ground squared. So that's the magnitude squared. So to get the magnitude, remember the magnitude of a vector, if you have vector A squared is the same as like this, and it is equal to vector A taken the dot product with itself. So exactly that's what I'm going to do. Vi relative to the ground squared will equal to Vi relative to the ground dotted with itself. Vi relative to the ground dotted with itself. This vector dotted with itself. But this vector is these two vectors added together and then dotted with themselves. So it's Vi relative to the center of mass plus Vi, V center of mass dotted with Vi relative to the center of mass plus V center of mass. Let's take the dot product. Dot product of Vi relative to the center of mass is Vi relative to the center of mass squared. Right? Dot product of a vector with itself is just that vector squared, the magnitude squared. So it's Vi relative to the center of mass squared plus, we will get two of these. Vi relative to the center of mass dot the velocity of the center of mass, and V relative to the center of mass dot Vi, but the dot product, the order doesn't matter, you just get two of them then. So you get twice V center of mass dotted with Vi relative to the center of mass. Plus, now V center of mass dot V center of mass is the velocity of the center of mass squared. So this is just Vi relative to the ground squared. I'm going to take this Vi relative to the ground squared and I'm going to replace it here. And let's see what happens. Okay? And I will come back to the whiteboard again. So I need this. I'm going to copy it. Oh, I don't need the vector sign here. I'm going to copy this and paste it right here. So let's see. So total kinetic energy is equal to 1/2 times the sum of mi times a lot of stuff, some stuff. Vi relative to the center of mass squared. Vi relative to the center of mass squared plus V center of mass squared plus 2V center of mass dot Vi relative to the center of mass. V center of mass dot Vi relative to the center of mass, like so. Okay. Next, what should I do? Well, we have to expand this a little bit. So I get the total kinetic energy would be 1/2 mi Vi relative to the center of mass. Sum over mi Vi relative to the center of mass squared plus 1/2 V center of the velocity of the center of mass is constant. It doesn't see Vi is here. Each little mass element may have a different velocity, but the center of mass has only one velocity. So that could be pulled out of the summation. So we'll have 1/2 of V of the center of mass times the sum over mi. Center of mass squared times the sum over mi. So this is this part, 1/2 mi V center of mass squared. And then plus 1/2, again, V center of mass could be pulled out. And we take the dot product with, I have mi Vi center of mass. Mi Vi relative to the center of mass, like so. What happens is, this will be 0, and we will see why. This part will just drop. It will be 0, and it will be just the sum of these two parts. I will show you in a moment why this is 0, but let's talk about what these are. So I have the kinetic energy equal to 1/2 what? We'll get to this one. And then, so 1/2 plus the sum over mi Vi relative to the center of mass. So take this Vi relative to the center of mass. What is the velocity of this? So here's the center of mass. Here's the center of mass. Take a point here. When the object rolls, this point, let's say a little bit later it will be here, so it only rolls relative to the center of mass. So what is its velocity? Well, its velocity will be its distance from the center of mass times omega. So the velocity of this object relative, the velocity of an mi relative to the center of mass, Vi relative to the center of mass will equal to how quickly the object is rolling times r relative to the center of mass. So it's omega times Ri relative to the center of mass. That's what this is. So here I'm going to replace this by, because the object is rigid, this point cannot get farther from the center of mass. It can only rotate about the center of mass. It cannot get any farther. It's rigid. Remember, rigid body points don't get closer or farther away from each other. They can rotate about each other as a whole body. But imagine you're here at the center of mass. A moment ago it was here, but then as it rotated, you're still here, but this point is here relative to you. So it only moved at an arc. And the arc, the length of this distance is Ri relative to the center of mass, and how quickly it's spinning is omega. And so we get mi, and then this I have to square it, so it becomes Ri relative to the center of mass squared, and then omega squared. So I'll put the omega squared outside, because it's also, see, it doesn't have a subscript I. Everybody's spinning at an omega, so you can pull it off the summation. And then plus 1/2. What is this mi? When you add all the mi's together, the sum over mi, that's just the total mass. So it's 1/2 the total mass times the velocity of the center of mass squared. And this part is 0. I will show you why it's 0 in a moment. Now, the kinetic energy will equal to, let me put this part here first. 1/2 the total mass times the velocity of the center of mass squared plus, what's this? What is mi ri squared relative to the center of mass squared? That's the moment of inertia. Remember the moment of inertia for a body? It was, you take the mass of that body and it's the moment of inertia relative to the center of mass. So you take the mass of that body and how far it is from the center of mass squared, then you add them and you get the moment of inertia. So it's 1/2 the moment of inertia, I put here the moment of inertia relative to the center of mass omega squared. So it's nicely broken. Remember, 1/2 mv squared plus 1/2 I omega squared. That is the total kinetic energy. Okay. Now, why is this part 0? Well, this part is 0 is because of this part. So if I can show you that this is 0, then this whole thing would be 0. So why is the sum over mi vi relative to the center of mass 0? Well, let's see. So let me copy this and show you why it's 0. Mi vi relative to the center of mass. So let's see. The sum over mi vi relative to the center of mass relative to the center of mass. Why is this 0? Well, this is vi relative to the center of mass, so it's the derivative of ri relative to the center of mass. So it's equal to this. ddt of the sum over mi ri relative to the center of mass. So why is that 0? Well, what is ri relative to the center of mass? I relative to the center of mass will be ri relative to the ground minus r center of mass. So let's see. So let's replace it like that. ddt of the sum over mi. I will write this as this vector minus this one. ri relative to the ground minus r center of mass. Why is this 0? Well, let's see. ddt sum over, I'll break this sum into two different sums. So it will be mi times ri relative to the ground, and then minus the sum over mi r center of mass. Okay. Why is that 0? Well, it's ddt following two more steps over the sum over mi ri relative to the ground minus r center of mass times the sum over mi. What is the sum over mi? Well, that's the total mass. So it's the total mass times r center of mass. So you have ddt over summation mi, this is the vector sign, ri relative to the ground minus total mass times r center of mass. Okay, but what is r center of mass? Our center of mass is equal to this. So mass times r center of mass will give me this part. The mass times r center of mass is exactly this part. It's the sum over I equal to 1 to n mi ri. So it's the sum over mi ri when I multiply both sides. So ddt of the sum over mi ri relative to the ground minus, again, the mass times the center of mass. Well, that's just the sum over ri relative to the ground mi. Forget that. But this and this are exactly the same, so you get 0. It's 0. That's why this part here is equal to 0. Let me show you how we can use this. So now, let's say, I don't really like all this math, and I don't care much for it. That's fair. But I want to show you now, show me what I need to know. This is what you need to know. You need to know this one. So let's say I ask you to find the kinetic energy of an object that's rolling, okay, of a radius r. So let's do an example. Let me erase the board. And let me actually check how much time has passed. Yeah, 20 minutes. So let me erase the board. So here's an example. A disk of mass capital M equals to 1 kilogram and radius r equals to 0.1 meters is rolling without slipping. The disk travels at constant speed and moves 15 meters in 3 seconds. Find the kinetic energy of the disk. Oh, disk is with a C. So here is a disk. The disk is here. It's rolling without slipping. It has radius r. It's moving at constant speed to the right, let's say, and it moves 15 meters in 3 seconds. So after 3 seconds, it has moved here. So this is 15 meters in 3 seconds. So V, so the center of mass has moved from here to here in 3 seconds. So V, center of mass, will be the distance over time. So that's 15 over 3, and that's 5 meters per second. It's a disk. So whenever you do rotational motion and you're given the radius and everything, you might as well calculate the moment of inertia. So the moment of inertia of the disk about the center of mass is 1/2 mr squared. It's something you can look up. So it's equal to 1/2. The mass of the disk, 1/2 mr squared. Let me leave it as 1/2 mr squared. That's fine. We can, actually for the sake of this problem, let me get it. So it's 1/2, the mass of the disk we said is 1 kilogram, and r is 0.1, and you square it, so you get 10 to the minus 2. So you have 0.5, which is the 1/2 times 10 to the minus 2, which is equal to 5 times 10 to the minus 3. That's the moment of inertia. So the total kinetic energy will have 2 parts: the kinetic energy due to translation plus the kinetic energy due to rotation. Kinetic energy due to translation is 1/2 the mass times this velocity of the center of mass squared plus 1/2 I omega squared. And I is understood to be the moment of inertia about the center of mass. So here I get 1/2. The mass is 1 kilogram. The velocity of the center of mass is 5, not 3. 5, so 5 squared plus 1/2 I omega squared. So I get I is 5 times 10 to the minus 3. And how much is omega? Well, we know that V is equal to omega r. So omega is V over r. So it will be, V is 5, and then r is 0.1, so it's 50. So it would be 50. So that's 5 times 10 to the first power, and you have to square it. And so you get here, what, 25 over 2? 25 over 2 plus Here you have 5 times 5 times 5, that's 125 over 2. So 125 over 2. But then I have 10 to the 1 and 10 to the minus, 10 to the 1 squared is 10 to the 2 times this one would be times 10 to the minus 1. So you get 12.5 from this one plus 10 to the minus 1 times this is 12.5, so it's 12.5 over 2. And you get the number of joules. Okay, I don't want to spend more time on this. Now, there is a nice way to actually derive this without going through all the work that I did. And that nice way is to observe that as this object moves, right, it's moving to the right at a v, and it's spinning at an angular velocity omega. So the velocity of the center of mass, v center of mass, is equal to omega times r. And we have to realize that this point here is in static, instantly has zero velocity. So to see that, take a wheel, let me see here, like a wheel here with spikes like this. And imagine it's rolling over those spikes. So it just rolls over the spikes. So the instant this is here, it has zero velocity, right? You can imagine it's in contact with the ground, and it will be at zero velocity until this one hits the ground, and then this one will be at rest. So the whole wheel is as if it's rotating about this axis, an axis through the end. So it's as if the entire thing is it's a pure roll about this instantaneous axis. And if it's a pure roll, we know that the kinetic energy is 1/2 I omega squared. And omega is just this, omega, because the center of mass is a distance r, and so omega is v over r, which is omega r divided by r, that's omega. And so you get 1/2 I omega squared, but the moment of inertia here is not about the center of mass. It's spinning about this axis here that's at the end. But that's fine. We can use the parallel axis theorem to derive it. We say that the moment of inertia about this axis will equal to the moment of inertia about the center of mass plus mr squared. The total mass times this r squared. And so we get the following. We get 1/2 I about the center of mass omega squared plus 1/2 of m, and then r squared omega squared is the velocity of the center of mass squared. So you get the velocity of the center of mass squared. That's the kinetic energy, which is this one. You can derive it that way also. But I think it's trickier. I left it, did it the honest way first. Well, this one is also honest. But, and then I showed you this one. Sounds good. We will move on. I wanted to quickly do an example of an object rolling down a hill. So imagine you have an object here. The height is h, and it's here. V initial is equal to 0, and then it rolls down, and then it's spinning and moving this way. So what's the velocity here? Well, you use conservation of energy. The total energy here is mgh. That's it. It doesn't have any kinetic energy. The energy here is 1/2 the total mass v squared, the velocity of the center of mass, plus 1/2 I omega squared, I times omega squared. And remember, the moment of inertia is always something, it's mr squared times some constant. That constant could be 1/2, it could be 1, it could be even 0 if it's a point mass, it could be 2/5 if it's a solid sphere, and so on. So I would replace the moment of inertia by some constant times mr squared. So I get mgh equals to 1/2 mv squared plus 1/2 a constant times mr squared omega squared. Notice the mass simply cancels from everywhere, so we get gh equals to 1/2 of v squared plus. Now, r omega is v, so r squared omega squared is v squared, so this is 1/2 c v squared. And you can multiply both sides by 2, so you get 2gh equals to v squared plus cv squared, which is 1 plus the constant times v squared, and therefore v will equal to 2gh divided by 1 plus c, the square root. That's how you would deal with these problems. I did it quick, but we might do one in the homework. All right, so the next thing I'm going to go to more vectors, and we will talk about the angular velocity vector and the angular momentum vector. So we'll do more cross product. All right, see you in a minute.